Before moving on, let's look at some additional examples of formulas and find the scopes and tree structures of their operators. Let's start with the formula P implies not P is equivalent to not P. Well, if we restore some parentheses, the scopes of the operators become obvious. This not has that P for its scope, and this not has this P for its scope. This implies has P implies not P as a scope, and this if and only if, or is equivalent to, has the whole formula for its scope. So if we draw our tree, we start with is equivalent to, and on the left it has an implies, to the left of that is a P, to the right of that is a not, with a P attached. To the right of our if and only if, or is equivalent to, we have a not, and attached to that not is a P. So that was all well and good, but let's look at something a little more complicated. Let's try the formula not P and Q is equivalent to R and not P or Q implies R. If we restore some parentheses, it gets a little bit easier. We can restore parentheses here, and since we know that not ties more closely than and or implies, we can restore parentheses here for our convenience. And we know that the and ties more closely than the implies, so we can put some parentheses here. And then we know that the implies ties more closely than the is equivalent to, so we can put parentheses around this whole side. So we see that our is equivalent to is at the top of our tree, and to the left is an and, to the left of the and is a not with a P attached, and to the right of the and is a Q. To the right of this is equivalent to is this implies over here, because this and is bound and ties more closely than the implies. So we write our implies, and then to the left of the implies we have the and operator. To the left of the and is R. To the right of the and is a not with a not attached, right, because these are outside of the parentheses. And then beneath the second not is an or with a P and a Q on the sides. To the right of our implies is just an R. So as you can see, these formulas can get fairly complicated fairly fast. And this is why logic, or one of the reasons why logic can be a much more difficult discipline than a cursory understanding of truth tables would lead you to believe, is because once you have a few formulas or a few connectives, it can become arbitrarily complex. But with that note, let's take a step towards truth tables.